Hello everyone, welcome to CYBR601, Introduction to Cybernetic Modeling and Simulation, Learning Activity 5, Numerical Simulations. And this lecture we'll go over concepts and applications. We're going to go ahead and get into it by going high level into what is a numerical simulation to begin with. So let's go ahead and start with, let's get this on the road. And start off with a definition from Portfolio. Nature Portfolio, actually. It has a very, very good definition of what a numerical simulation is. You'll actually see a lot of different simulations, numerical simulation definitions. But this is one that I think more broadly encapsulates many of the definitions. So it's a numerical simulation is a calculation that run on a computer. Perfect. And then a piece of this that is really important, and then we'll see as its main importance, is a numerical simulation should have, for all intents and purposes, a underlying mathematical model. And I guess it doesn't necessarily need to be physically informed, but most of the time, the mathematical model is physically informed. And we'll talk a little bit more about what that means and what the ramifications for that are. But for the purposes of what we're trying to do here, and again, I'm not trying to get too far into the fringes. We're sticking to what the predominant body of work as it relates to numerical simulations within the modeling and simulation field. So this is a great definition for that. And a big thing is it's one of the big parts about any simulation, not just numerical simulations, but any type of M&S activity, is its main focus is to provide a simulation that is too complex for the human to contemplate or envision or imagine. And we can imagine quite a bit as humans, but the reality is that there's an extent to what, there's a limit, and it doesn't take much to exceed our limited capacity, even in totality, in total as the human race, to exceed our capacity to think into the future or simulate things that are beyond, most of the times beyond what we can see. So this is a good high level. This is very good. And let's go ahead and jump over to the right here and talk a little bit about mathematically what we're talking about. This is just an example. This is one of the examples. We'll actually explore this in more detail. We won't be doing any mathematical work here. This isn't that type of course. But we will be exploring in this case the core of this being numerical simulations, and at the middle of that being equations. At the middle of this, in this case, is an n-body equation. And in this case, it's a two-body problem, and it describes a physical system, and it uses an equation to describe a physical system. So this is back to a numerical simulation. In that a equation, mathematical model, is at the core of it, and not only that, but it approximates a physical system. In other words, this equation, in this particular case, these two set of equations, solve for a two-body problem and how gravity behaves between the sun and the earth. Okay, so let's talk about why is this even, we're talking about this theoretically, and we're going to only spend a couple slides on theory. But why is this such a big deal? So let's run into why this is such a big deal. So you take your n-body problem, right? And I think, and when you think about it on paper, and if you think about it in terms of a two-body problem, fine, we can solve that. A three-body problem, we can solve that too. And it really can be worked out on paper, and it can even be hard to work out almost in a cartoon. In other words, if you drew it out hand by hand, frame by frame, and you put it on a piece of paper, and then you work this n-body problem out over a series of slides, so to speak. Old school, you could create a cartoon of this back in the late 1800s. The theory for classical mechanics and Newton's gravitational work that he had done back in the 1700s certainly hold true to today, to a certain extent, when you're doing anything that's classical two-body problems. And then, of course, Einstein for any of the other type of work that you're looking for special relativity, general relativity, and relativistic effects as it relates to cosmology. But the problem is when you talk about these things and you try to say, hey, you try to take all that and you put it in, it's just too much for us to put on a piece of paper. Even in the 1800s, the 1900s, and then, we didn't really start to have the computational capability to really get into a situation where we could say, well, what did it look like for 100,000 bodies, 1 billion, 4 billion, trillion bodies? There's just no way that you could have humans sit down and put that on paper and then simulate that out and all these massive data points. So there's a perfect example of this, a box of Universe, an American Scientist. Very good read if you're interested in learning more about cosmology and then simulation as it relates to cosmology. It's a very good article, high level, great for the casual casual person that's interested in astronomy like myself. Big into it, and I do not profess to know anything about. I don't do it for a living. It's one of those things I love to just read about. So you'll see as we move through this, stuff about space will permeate through our M&S course. But it's a very good article. Highly recommend reading it. Okay, next up. So as we move on, cosmology is fine, right? And that's okay for the big stuff, right? Of course, we understand, these gravitational. When we talk about gravitation, especially at that scale, we're talking, billions of light years, and in terms of volume. We're talking a volumetric that's huge, right? But if we reel it back a little bit and try to say, okay, well, how about something that's a little bit more pragmatic? Well, I totally agree. There's, modeling and simulation for something that's a little bit more pragmatic. Well, let's talk about something just recent. And I say recent within the last, 120 years. But if you back up to the Wright brothers in the early 1900s, the way they tested back then, and we still do this, it's trial and error, A/B testing strategy. You build one and you build another, and then you see which one works better. Or it's just a A1, A2, A3 testing strategy, right? Where you build one, that didn't work, play with it, and build another version of it, right? And that's essentially the way the Wright brothers worked. Back then, it was you build it, and then you tested it, and then you keep iterating on building and testing it, and then breaking things. And then, but it was very expensive to do it back. Even today, right? It's so expensive to build something, put it out in the field, and then watch it be destroyed. A prototype, right? We're talking about prototyping on something physical. And that's where modeling and simulation comes into play. Even though we still do it today, with 3D printers, we can get away with mock prototyping. That didn't work. Let's put another print model together. It's something that we do, and we'll never quite fully get away from physical iteration, the physical iteration of products, right? There'll always be a little bit of that. But when we start to talk about really big things, like we're building tanks or aircraft carriers or airframes or anything like that, it becomes more, even if it's a part of let's say, part of an aircraft, let's say just the wing. Well, it becomes really it becomes expensive because you talk about the composites that go into it. Let's say it's a really advanced aircraft and we're trying to make it lightweight. Well, composites are expensive, especially advanced composites. So, and same thing with cars, right? If we're building a lightweight car, well, if we're building a new hood for a car, that could be thousands and thousands of dollars, and to let's say you're using that for applications as it relates to, let's say, crash testing. Well, every time you build a new hood, that could be 10, 20, $30,000 out the window, especially if it's an advanced composite. So that's where modeling and simulation comes into play. So let's talk about that. So in general, when we're talking about modeling and simulation, before we jump into numerical simulations a little bit more, back to testing a car, right, and the crashing of a car, we can actually prototype that virtually. We don't have to go take a car and put it through its paces, put a new hood on it. Just using an example, putting a new composite hood on a car to lower its weight, and then see how the crash testing goes. Physically, we don't have to physically do that. We'll eventually physically do that, but it's so much cheaper to do a virtual prototype and create using computational technology we have today to simulate, to model out the new hood, and then simulate it over time, crashing into a structure. It's a lot more cost effective to do that. So if you're interested, there's actually a neat little link. As I was kind of poking around to kind of enhance the modeling and simulation course, I found this handy little link over here. GD Tech, they talk a little bit about numerical simulation, and I found it kind of nice. A couple little tidbits of info that you might be able to pick up. So that's another area you might feel free to peruse. Okay, so going, taking it to another level, that's crash testing. And from an applied perspective, let's talk about an airfoil. So back to the Wright brothers, let's talk a little bit about not just the concepts, the abstract concepts, but the applications. So the Wright brothers had put you got to create a wing. And it's pretty complicated. Back then, there really wasn't anything outside of essentially basic fluid mechanics to simulate air as it moves, or calculate how air moves over an airfoil. A lot of it was just, again, trial and error. How do we build a wing? What's the best way to build a wing? And then, of course, that was iterated over time. And has become very advanced now. We have so much data, and we're consistently making airfoils better, not just for wings, but for all wing surfaces. That goes into propellers, because a propeller is a wing surface. The airfoil, just the wing itself, of course, is a surface. But a lot of it now is getting into stealth technology and the stuff that's printed on it and painted on it, and all kinds of fun stuff, and what you can embed in it, how you can morph it. There's quite a bit of research that goes into it. So keeping it high level, though, it's not just a single equation. A lot of times, especially when you're talking about more modern views of modeling and simulating an airfoil, it's literally hundreds of equations. We're talking a lot of equations. It's just not just one equation to rule them all as it relates to airfoils. There's different shapes, different sizes, different aspects. In this particular case, we're looking at many different equations that go into modeling airflow as it relates to optimizing and or classifying. I should say that too. Airflow over an airfoil. And this is just a 2D view of a main part of the section. Now take this and expand upon this over the body of the whole wing. I'm not talking about the body of the airplane, but just the body. Most everyone here has probably ridden in an airplane. When you look at an airline, a standard 727, let's say, the almost all tube wing and tube designs that you look at for modern day airplanes that we ride in, they're a lot thicker and bigger as they ride up to the base of the body. So the wing is a lot bigger, and then of course the wing becomes much smaller. Well, to a certain extent, it has to because of just the structural integrity of the wing. The integrity, I mean, it has to be lighter at the tips than it is closer to the body. That doesn't say it always has to be that way. There's different designs that engineers, aerospace engineers, are always working with. But where I'm going with this is this particular model. Even though there's many equations that go into modeling and simulating the airfoil, that's why I say there's hundreds, because there's even more that get involved when you talk about the 3D aspect of it. This is just a 2D view. Okay, so one more thing before I talk about Krishnamurthy real quick, but when we talk about modeling and simulation activities, there is also a piece of it that is similar to machine learning, in the sense that when we're modeling and simulating, we could be doing it as a goal output for classification. In other words, we're just clustering and or classifying, and I won't go into the differentiation between clustering and classification. That's more of a that's more of a machine learning exercise, and we will talk more about that, but I do want to stick to the modeling and simulation nomenclature for the time being. So high level, we can model and sim for optimization, or we can model and sim for classification. Optimization is looking for more efficiency out of a structure. Classification is just to identify the parts of the structure, right? We can simulate for classification, or we can simulate for optimization. So there's two items to think about there. Okay, next, when you get to Krishnamurthy, as it relates to the airfoils and meshing of airfoils, it's an excellent read. So I highly recommend. You can just skim through it. Don't spend a ton of time on it, but it's a fun read. You'll get an idea of how complicated it is, just to see what that looks like. As an example, just to see what that looks like, let's go to the next slide. So when you go and take a look, and again, I'm taking snippets, but for modeling and simulation, you can use different techniques to simulate for optimization or classification of a given structure or environment or what have you. So we can use different techniques for the same thing. And I am not, again, not to profess that I am not a fluid dynamicist. I'm not in that space. But you can see that there are very clearly, there's different modeling strategies. There's an O-type, which uses kind of an ordinal, or I should say what am I looking for? It's kind of like a radial pattern. That's what you've got a radial pattern. And when you look at H-type, it's kind of got a more linear a view of the world. And they're doing modeling from two different perspectives, and it creates two different simulation patterns. And if you're interested in learning more, there's a link here. Definitely a good read. Now, again, this just the big takeaway is that there's different techniques for modeling the same thing and simulating the same phenomenon. Okay. So a question you might be asking yourself from a numerical simulation, and we'll definitely get to the different aspects of what is even the different components of a numerical simulation, but they're usually physics informed. So we've talked about that. They have a mathematical property that is physically informed. And again, I'm not getting into the fringes. That's just, for the most part, for all intents and purposes, for us here in this course, just know that they're numerical simulations, mathematically focused, and physically informed. And then in this case, we're going to be using, for our lab, we'll be using an n-body simulation. And an n-body simulation, as an example, and I mentioned it briefly, is Newton's law of universal gravitation. It was hammered out back in the 1700s, late 1700s. And then Einstein's theory of general relativity, as well as special relativity. Those were those were created in the 1900s, early 1900s, so 1905, 1915 timeframe. Okay, so one other bit of info, and I will be talking about this in a little bit more detail as we get towards the end of today's lecture. Mathematically oriented, that's what numerical simulations are, but and because they are mathematically oriented, there is a special emphasis on stochastic, deterministic, or both. So I'll talk about what stochastic versus deterministic means, but I will say this: stochastic versus deterministic really has an impact on all simulation types, not just numerical simulations. But there is an added emphasis because stochastic systems, deterministic systems, especially when it relates to numerical simulations, they take on added emphasis. All right, so let's jump into the numerical simulation architecture. So you're probably interested in, and I know I am, interested in what goes into a numerical simulation architecture. There are some things here that you could probably argue that this is just simulation architecture in general, high level, super high level. But I will say this, as it relates to numerical simulations, there's of course going to be some shared architecture with other simulation types, and we'll try to stay faithful as we move through this in terms of what numerical simulation architectures look like as it relates to other architectures, and because this does have an impact on your following class after this, which is your architecture course, and that's more broad and more technologically focused architectures, but it's good to know. All right, so numerical simulation architectures. In this case, I see it in kind of three big buckets. There's an information portion, a computation portion, and then a virtualization portion. You're going to find different architectural types out there. And again, it just depends on, you can spin these different ways, right? But high level, I think you're looking at probably three big buckets. On the information side, you've got a physics-informed mathematical equation. You've got simulation parameters, and you have initial conditions. These are all what I call the information part of it. And then if it's a more advanced simulation, and let's say there's an embedded AI within it, and you get you might have an external data component, but again, it just depends on what you're trying to do. So these are the high level components. Computation, computer hardware, operating system, and then the software that sits on top of that. Pretty straightforward. I wouldn't go into too much more detail other than that. I will say that when we talk about static versus dynamic, that does have an impact on what type of software. There's a lot of different types of software. Some software are purpose-built. Some are more generic. In our case, we're using generic MNS software, which is the Anaconda framework, as well as Microsoft MakeCode, as well as Unreal. These are all three software packages that are generic that can be used for multiple MNS activities for the development of really complicated to advanced, all the way down to really basic. There are modeling and software packages that are specific to a given kind of function. For example, computational fluid dynamics, where you're looking at the flow of fluid over, let's say air, and the aerodynamic capability of a car, or its ballistic coefficient, so to speak, through air. Or maybe you're looking at the ballistic coefficient of artillery through the air, right? That's very much something that the Army looks at. So there's all kinds of different, and there's different software packages for that specifically. Okay, what we're going to be using today is going to be your more general purpose package. So Python and Anaconda. All right. So in your third bucket, you got virtualization. This is the simulation. This is putting it into practice. So this is taking the information and using computation as a middleware, so to speak, even though I hesitate to use that word, especially for the computer science people, the computer systems people that are out there. It's kind of, maybe the middle tier is the better word to use instead of a middleware. But the middle tier of this in the computational world is the engine that drives the virtualization that we see. That is the simulation. That's the output. And from there, I think we can talk through what our final project. Just a note, one thing that as we move through this, I will make notes as it relates to your final project, and we'll be looking to, because your first year, you're getting into the grad program. This is a Master of Science in integrated systems design and dynamics. That design and dynamics piece of it, as well as integrated systems. It's a research. It's got a heavy research component in the degree, and so that also means that we also have to start flexing our writing muscles, and we're gonna tee up, because for many, CYBR601 is your first your grad course, your first grad course in this program. So we're going to create, it won't be a really long paper, but there will be a writing paper, and it'll be a simulation architecture paper. And I'll be dropping hints and dropping more information, but I do want you to be on the lookout. I'll probably be publishing a template here in the next couple of weeks for that final project, so you have some time to be thinking about it. And actually you can start making notes, and I can start to help fill information in. But this will also flex our APA writing format. That's what we'll be using. But to put a bow tie on this final project, just put a pin in it rather, because we'll circle back on this as we move along. Is our final project is going to focus on simulation architectures, comparing and contrasting. And just doing that, and not asking you to create a research plan or a research agenda or a research question. It'll be a comparing and contrasting of simulation architectures. So as we go through all these different architectures, there'll be a short paper, about 5 pages, and then APA format. And so be on the lookout. So it'll be 5 pages of body, 7 pages total. It'll be a cover page with a reference page at the end to capture your APA stylized references, and then an analysis of comparing and contrasting simulation architectures in the middle of it. So again, more to look out. Rather, let me rephrase that. More to come on that part of it. So definitely be on the lookout for that over the coming weeks. Okay. Let's get to terminology. Okay, so a piece of this is related to our readings. When you look at the DoD 5006-1, it's a very short paper. So go and download that. Go and as a part of an assignment, we'll talk about that at the end here today. But you will have a definition of information, computation, and virtualization. And then let's get some terminology standardized. So model, what is a model? So a model is a physical, mathematical, or otherwise logical representation of a system, entity, phenomenon, or process. And so this is it's pretty straightforward. That's a model. And then if you look on the right-hand side, it's the virtualization. That's a simulation. A simulation is a method for implementing a model over time. So that's, I love the way the DoD just abstracts that and makes it super simple for us to understand. So I gave you the very technical information, computation, virtualization. DoD likes to step in and makes things a lot easier for us to understand. So model, right, is based on, it's an information construct, right? It's just an information representation. That's what a model is. And then a simulation is just a virtualization of that model over time. Now, they didn't put this in the middle an engine, so that you won't find engine in the DoD language. I'm putting that in there because the computational, the hardware, that middle layer, that middle tier that we talked about earlier, that's the engine. That's what makes this all work. That's what takes the model and turns it into a simulation. That's what takes multiple models and turns it into simulation. That's what takes millions of models and turns it into a simulation. Think of, I know I go back to this, but I'm going to go off the path a little bit. But think about the game Skyrim. I'd love everyone go check it out. If you're not familiar with Skyrim, there's tons of other examples. Think of Fallout. Think of the new. There's the game No Man's Sky. Think of the game Dark Souls or Elden Ring, the newer Elden Ring. All these games, and then the new Starfield that's coming out later this year. They all create what's called an engine in the middle of it, and they have millions and millions of models that are incorporated into the engine to create the simulation. So a game like Skyrim, it's a simulation. Think of Minecraft, it's a simulation. It has millions and millions, I mean billions of models, especially if you take Minecraft and pare it down to its base core, which is a block, a square cube. Well, it's got billions of cubes in it, especially the new Minecraft. And there's a computational engine at its core that makes that simulation run. Okay, so I think I've just about covered all of that. Again, this goes back to, this is a helpful tidbit of information as it relates back to, as you're making notes, back to your final project. Comparing and contrasting simulation architectures. Okay, so that's a bit of terminology. And then one more bit of terminology. We mentioned this in terms of stochastic versus deterministic. A stochastic, and again, this can apply to any modeling and simulation or simulation architecture. But a stochastic architecture, or an architecture that is rooted in a stochastic process, it leverages a random process. And deterministic is a system that is just like it sounds. It's deterministic. It's if this happens, then this happens. Whereas in a stochastic world, if a given event happens, multiple gradients can happen between a range of variables, or a range gradient, and then of course you can have both. You can have stuff where it's stochastic within a limit. In other words, it's stochastic with a predefined limit on determinism of what happens between a particular limit. I want to keep it high level because, again, we're not doing machine learning yet or statistics just yet. But for those that are in the machine learning and autonomous systems program, this will actually take on more importance. Those that are in the systems management option will also know that this can take on some importance as well as it relates to data analytics and analyzing different types of systems, whether they be Markovian systems from an economic perspective, or whether they be stochastic systems from a marketing perspective, or whether they're deterministic systems that are closed and they have finite logical inputs and outputs. Okay, I think that's enough for terminology. Definitely spend some time learning this. Again, it definitely plays into your final project. All right, so let's talk visually what the difference is. I think this will help kind of ground this out. I'm actually going to make this available for you. You don't. I'll have the code up, but I won't cover this in the lab. But this will be a little extra for you to kind of play with. This is something that I created to illustrate the difference between stochastic versus deterministic. Deterministic, that blue line, that's a sine wave. It's a standard sine wave, and that's to a certain extent what you're looking at here is a very, very basic numerical simulation. And so we're using Python, and then we're plotting out. This would be considered a static a static numerical simulation. It's not dynamic. In other words, it's a one-time run. And you hit it one time, and then it does this on the right-hand side. So it plots out the sine wave in blue, right? And again, that's a physically informed phenomenon. But what I can do is I can overlay randomly points that follow or approximate those deterministic, that deterministic line. So there's the blue cyan dots. That's a stochastic process because it approximates. It's following the line, but it's approximately following the line. And that's the big difference between stochastic systems and deterministic systems. Stochastic systems have some wiggle room because they're based on probabilities. Deterministic systems do not have any wiggle room. And in this case, taken together, this is a hybrid system. This is when we combine the deterministic and the stochastic in the same system like we have here, it's actually a hybrid system. So it has a deterministic feature, but with illustrated stochastic overlaid on top of that deterministic feature. And if you want to learn more about this, again, this is something we'll spend a lot more time in the machine learning piece of it. But if you aren't in the machine learning and autonomous systems option, that's okay. If you want to learn more about this, hit me up. I'm definitely your person in terms of the stats and machine learning piece of it. Okay. So I think that wraps up the lecture. Let's go ahead and jump into the lab. So our lab, I'm gonna to give you a heads up. We're going to be for the lab, we're going to be doing an n-body simulation. The reason we're going to be doing an n-body simulation is because it mirrors up very nicely with the concepts we talked about here in class, in the lecture rather. And then what do we need for the lab? You'll need Anaconda Navigator, and then you'll need Spider. That's also part of Anaconda Navigator. It's over here. It'll get downloaded. These versions might be a little different, but that's okay. And then you'll need my code, and that's actually going to be, I'll show you where it's at. It's actually in Canvas under Lab Materials. My Python code's there. My Python code is actually also there. For this code here is also in the lab materials, so you can run this and see how it happens. You can run it over and over again. You could actually, if you were so inclined, you could put this into a loop and have it run 30 times, 100 times a second, and then it would kind of give you a nice movie, so to speak, of this sine wave behaving over time. And you won't see a change in the sine wave, but you'll see a change in the stochastic. The cyan dots are going to change. And that perfectly illustrates the difference between deterministic versus stochastic. In other words, over time, deterministic machines always behave the same. Regardless, each iteration, they're always the same. Stochastic, there's some wiggle room for play. So those cyan dots will move each time in the lab. But that's something that you can play with. I'll let you run around with that. That code is for you to be able to play with. And I'll show you how to load code up into Spider. Pretty straightforward. Okay, again, you don't have to be a programmer. Just familiar with PC software and how to load up a program. That's all you need to know. All right. And then this week is a little different than last week. Last week was just follow-along labs. This week we'll have a follow-along lab. But I also have Microsoft Make Code. So let's talk about the labs in a little bit more detail. So week 2 labs, they're in Canvas modules. There's going to be a couple ones. There's going to be one for where's everything at, how to get things installed. I'll run you through that. There'll be a separate lab for the n-body simulation. And then I'll have a separate lab rather for the Microsoft Make Code. The Microsoft Make Code for this week is going to be a star field generator, and you will build this on your own. This isn't something that I'm going to walk you through. So I'll walk you through the n-body simulation, and I'll tie that back to the different aspects of the simulation architecture. But for Microsoft Make Code, I want you to build it out. So the good news is Microsoft Make Code has a tutorial for how to build a star field. And after you finish the star field, I want you to, and because this has direct impacts, this is why you have to, I want to impress upon you, do not try the Microsoft MakeCode sessions, because these are going to be, as we go through, these are going to be used to illustrate, to help you understand the differences between what it is that's happening in the follow along, the n-body simulation, and how the star field generator in this case is different from the n-body simulation. These questions will a good mature answer, in other words, one that you've really thought through, is going to exhibit itself in the final project, because you want to make notes around comparing and contrasting between different architectures. What similarities are there as it relates to whether it's stochastic or deterministic? Is the star field generator deterministic, or is it stochastic? I'm not going to answer that for you. I want you to think about it, and I want you to look through the MakeCode to kind of get a feel for like the differences. Are there other differences that you can spot? And in other words, as you look through the lecture material, what other areas do you see that could be differentiators between n-body simulation and the star field generator? Okay, last up for this week, I want you to read pages 9 and 10 of the, just to kind of reinforce the M&S terminology. 9 and 10 of the 5000.61, the DoD instruction, modeling and simulation, verification, validation, accreditation. Download that, take a quick look at it. It's not really long, it's pretty short, but I just want you to read through that to get reinforce the modeling and simulation terminology. And then a shout out for this week. You will have your first quiz that's coming up. And that's something that I will be releasing a little bit later this week, but that'll be our first assignment that'll be coming up. And if you have any questions, feel free to reach out to Dr. Jackson or myself. And I believe, I think that's all we have. So thank you for staying along, and I will see you in the lab.